The concept of time before the Big Bang is a fascinating topic that challenges our understanding of both time and the universe itself. Scientists often say that time, as we know it, began with the Big Bang, which occurred approximately 13.8 billion years ago. Before that event, discussing time becomes tricky, because if there was no universe, then how could there be time? The Big Bang marks the beginning of space and time, so any notion of before may not even have meaning in our conventional sense. This idea stems from the theory of general relativity proposed by Albert Einstein, which suggests that time and space are interconnected and form a single fabric known as space-time. Some physicists propose that before the Big Bang, there could have been a different kind of existence, perhaps a state of singularity, where the laws of physics as we understand them break down. This singularity would not have had time in the traditional sense, as there were no events occurring to measure it against. Other theories, like the cyclic model, suggest that the universe goes through endless cycles of expansion and contraction, so perhaps there was a time before our current Big Bang, but it was vastly different from the time that we experience now. There are also ideas floating around regarding quantum gravity, which attempts to unify quantum mechanics and general relativity. Some researchers believe that the universe may have existed in a quantum state before the Big Bang, where time could have behaved differently, possibly existing in a form that we cannot perceive or understand. Theoretical physicist Carlo Brevelli has proposed the idea that time may not be a fundamental part of the universe, but rather an emergent property that comes into being at certain scales. In this view, time might have no meaning in the extremely small scales of the quantum realm, where particles exist in a probability state rather than in a fixed time frame. Adding to the complexity, there are models like the no-boundary proposal suggested by Stephen Hawking and James Hartle, which posits that the universe is finite but unbounded, meaning it does not have a boundary or edge, and thus time could be viewed as having no beginning or end. In this sense, time before the Big Bang could be envisioned as a sort of smooth, timeless existence, making the concept of before itself obsolete. Furthermore, the concept of time is often tied to entropy, a measure of disorder in a system, which increases over time according to the second law of Contra, in the context of the Big Bang theory. The traditional understanding of time is quite fascinating, as it suggests that time itself began with the Big Bang, around 13.8 billion years ago. Prior to this event, the very concept of time as we know it did not exist. There was no before the Big Bang, since time and space were created simultaneously in that explosive moment which marked the birth of our universe. According to this theory, as the universe expanded and cooled, time began to flow, leading to the formation of the fundamental particles and the eventual creation of atoms, stars, and galaxies. This idea challenges our everyday perceptions, where we often think of time as an endless continuum. But in the realm of cosmology, it is intimately tied to the fabric of space itself. As the universe continued to expand, the nature of time also evolved, with different regions of space experiencing time at varying rates due to the influence of gravity, a concept known as time dilation, which is a key aspect of Einstein's theory of relativity. In essence, the Big Bang theory proposes that time is not an absolute entity, but rather a dynamic aspect of the cosmos, shaped by the universe's expansion and the gravitational forces at play. This revolutionary perspective on time offers profound implications for our understanding of the universe and our place within it, as it suggests that the unfolding of time is intricately linked to the very existence and evolution of space and the matter within it. As scientists continue to explore the mysteries of the universe, the relationship between time and the cosmos remains a central question, pushing the boundaries of our knowledge and challenging us to rethink what we know about existence itself. The Big Bang, a term that often sparks curiosity and wonder, is defined by scientists as the event that marks the beginning of our universe. And interestingly, it also represents the beginning of time itself. This concept arises from the field of cosmology, which studies the large-scale properties of the universe as a whole. The Big Bang theory suggests that approximately 13.8 billion years ago, all the matter and energy that we see today was concentrated into an incredibly hot, dense point, often referred to as a singularity. At this moment, space itself began to expand rapidly, and as it did, it cooled down, allowing particles to form, which eventually led to the creation of atoms. Before this event, according to our current understanding, time as we know it did not exist. Thus, the Big Bang serves as a boundary, a cosmic moment that separates the universe's history from a time before anything we can comprehend. This definition aligns with the theories of general relativity proposed by Albert Einstein, which describes how space and time are interwoven into a single continuum. It challenges our everyday understanding of time, suggesting that it is not an absolute entity, but rather a dimension that is influenced by the universe's expansion. As the universe continued to expand, it created a vast tapestry of galaxies, stars, and planets, forming the rich cosmos we observe today. The cosmic microwave background radiation, discovered in the mid-20th century, serves as a remnant of the Big Bang, a faint glow that fills the universe and provides critical evidence supporting the theory. Scientists interpret this radiation as a snapshot of the early universe, a time when it was just a few 100,000 years old, revealing information about its hot, dense beginnings. Moreover, the Big Bang theory is not just a single event, but rather a process, and it has given rise to numerous questions and theories about the nature of the universe, including the concepts of inflation, dark matter, and dark energy. Inflation, for instance, refers to a rapid expansion of the universe that occurred in the first moments after the Big Bang, smoothing out irregularities and leading to the large-scale structure we see today. Understanding the Big Bang also raises philosophical questions about existence and what came before it, if anything. Some researchers explore ideas such as multiverse theories, suggesting that our universe could be just one of many, each with its own distinct properties and history. This discussion invites a broader contemplation of the universe's nature. The implications of general relativity on the concept of time before the Big Bang are both fascinating and complex, as they challenge our traditional understanding of time itself. According to Einstein's theory of general relativity, time is not an absolute entity, but rather it is intertwined with the fabric of space, forming what we call space-time. This connection implies that the passage of time is affected by gravity and the curvature of space-time itself. When we consider the state of the universe before the Big Bang, we enter a realm where our conventional notions of time may not apply in the same way we experience them today. In general relativity, as you approach a singularity, which is a point where gravitational forces become infinitely strong, the equation suggests that time itself could behave differently. The Big Bang, often described as the beginning of our universe, is thought to be a singularity, where density and temperature reach extremes. The prevailing view among cosmologists is that time, as we understand it, may not have existed in the same way before the Big Bang. Instead, general relativity leads us to contemplate a scenario where time could be considered as emerging from the conditions of the early universe, rather than existing in a linear fashion before it. Some physicists propose that the concept of time may have originated with the Big Bang, meaning that asking about before the Big Bang could be a misinterpretation of the universe's history. In this view, the Big Bang represents not just a point in time, but a transition from a timeless state to a time-bound one. Therefore, the implications of general relativity suggest that our understanding of time is deeply connected to the very structure of the universe, and as such, it may be fundamentally different from our everyday experiences of past, present, and future. Additionally, when exploring theories like quantum gravity, which seeks to reconcile general relativity with quantum mechanics, the nature of time becomes even more enigmatic. Some speculative theories suggest that time could be an emergent property, arising from more fundamental processes at the quantum level, further complicating our understanding of the temporal landscape before the Big Bang. This leads to intriguing questions about the nature of reality, the formation of the universe, and the very essence of time itself. In summary, while general relativity profoundly alters our perception of time, especially in relation to the cosmos, it also invites us to reconsider what we mean by time before significant events like the Big Bang. The implications extend beyond mere academic thought. The question of whether time can exist without space is a fascinating one, deeply rooted in the field of physics and cosmology, and it leads us to consider the very nature of the universe itself. According to Einstein's theory of relativity, time and space are interwoven into a single continuum known as space-time. This means fundamentally that time cannot be fully understood without considering space, and vice versa. When we think about the Big Bang, which is the leading explanation for the origin of our universe, we encounter a moment when both time and space began to emerge. Before the Big Bang, it is believed that there was no time as we know it, nor was there space. Instead, all the matter and energy that would eventually form the universe were concentrated in a singularity, an infinitely small and dense point. In this context, the Big Bang marks not just the beginning of matter and energy, but also the creation of time itself. As the universe expanded from that initial singularity, space began to stretch and form, and with it, time started to flow. So, in a way, we can say that time and space are born together, inseparable from one another from the moment of the Big Bang onward. If we were to imagine a scenario where time existed without space, it would be quite perplexing, as time implies change and progression, which inherently requires a spatial dimension to take place. For example, you can think of how we measure time through the movement of celestial bodies like the Earth revolving around the Sun, creating our days and years. Without space for those bodies to move through, the concept of time would lose its meaning. Furthermore, modern physics leads us to consider the relationship between time and gravity, which is also a manifestation of space-time. According to general relativity, massive objects can warp space-time, affecting how time flows relative to that gravity. This relationship also emphasizes that time is not a standalone entity. It is deeply affected by the structure of space around it. Therefore, the idea of time existing independently of space raises profound questions and challenges our understanding of both concepts. The exploration of these themes continues to be a central focus for physicists as they seek to explain the very origins of the universe and the fundamental laws that govern its behavior. In summary, while the question of time existing without space is intriguing, our current understanding, based on established scientific principles, suggests that they are fundamentally linked, especially as we trace back to the quantum mechanics, delves into the fabric of reality at its most fundamental level, presenting a view of time that is quite different from our everyday experiences. In the early universe, time is thought to behave in ways that challenge our traditional understanding. According to quantum theories, particularly those related to the Big Bang, time may not have existed in the same way we perceive it today. In this context, time is often linked to the state of the universe itself, which was an incredibly hot, dense point before it began to expand. Some interpretations suggest that before the Big Bang, time as we know it, with a clear past, present, and future, may not have existed, implying that time could have emerged from the quantum fluctuations of the early universe. Furthermore, the concept of time in quantum mechanics is often described as being interwoven with the fabric of space, forming what is known as space-time. In this framework, time is not a separate entity, but is instead part of a four-dimensional continuum where the geometry can change based on the energy and mass present. Means that the flow of time can vary depending on gravitational fields and velocities, a notion that aligns with Einstein's theory of relativity. When we look at the universe on a quantum scale, time may not be linear, but rather a series of probabilities and potentialities that collapse into reality when observed. There are also theories, such as loop quantum gravity, which attempt to merge quantum mechanics with general relativity. This approach posits that space-time itself is quantized, meaning it has a discrete structure at the smallest scales, which could lead to a scenario where time behaves differently in the early universe compared to later epochs. In this model, time might emerge from a more fundamental layer of reality, suggesting that our conventional understanding is merely an approximation of a deeper truth. Additionally, researchers are exploring the idea of time symmetry in quantum mechanics, where the equations that govern particle behavior remain unchanged if time is reversed. This raises intriguing questions about the directionality of time, especially in the context of cosmic events that took place in the early universe. As particles interacted and formed the building blocks of matter, and after may not have been as clear-cut, leading to a scenario in which time itself was shaped by these interactions. In summary, quantum mechanics offers a fascinating perspective on the nature of time, particularly when we consider the early universe. It suggests that time is not a constant linear progression, but rather, cosmologists face a fascinating challenge when it comes to understanding the nature of time and temporal events before the Big Bang, mainly because the Big Bang is considered the beginning of our universe, and according to many theories, it also marks the start of time itself. One prominent idea comes from Einstein's theory of relativity, which suggests that time is intertwined with space, forming a four-dimensional continuum known as space-time. According to this view, before the Big Bang, the traditional understanding of time may not apply in the same way we perceive it today. Cosmologists often use mathematical models to theorize about the conditions that existed before the Big Bang. For instance, the concept of a singularity suggests that all matter, energy, and space-time were compressed into an infinitely small point. However, what existed or how time functioned in that state remains speculative, as the laws of physics as we know them break down under such extreme conditions. Some researchers propose that time itself may have emerged from this singularity, meaning that asking what happened before the Big Bang might not even be a meaningful question, as time, in essence, did not exist in a form we can comprehend. Another approach involves examining cosmic background radiation, remnants from the early universe. This radiation, which fills the universe and provides a snapshot of the cosmos just after the Big Bang, allows cosmologists to infer characteristics of the universe's earliest moments. By studying this radiation, scientists can gain insights into the conditions that led to the Big Bang, but it does not provide direct information about any events before it. Some theoretical physicists also explore ideas like cyclic models, where the universe undergoes endless cycles of expansion and contraction, suggesting that what we perceive as the Big Bang is just one of many events in an infinite history. In such a model, the distinction between before and after might become blurred. Each cycle could represent a different phase in the universe's timeline. String theory, another intriguing framework, posits that fundamental particles are not point-like, but rather tiny strings vibrating in multiple dimensions. This theory suggests that our universe may be just one of many, potentially with different timelines and events occurring simultaneously in other dimensions. In this scenario, the question of time before the Big Bang might involve dimensions or realms that we cannot directly observe or measure. By utilizing advanced mathematics, computer simulations, the concept of time before the Big Bang is a fascinating topic in cosmology. And while the Big Bang theory itself describes the beginning of our universe, some theories suggest possibilities for what might have preceded it. One prominent theory is known as the cyclic universe theory, which proposes that the universe goes through infinite cycles of expansion and contraction. According to this theory, after the Big Bang, the universe expands for billions of years, then eventually slows down, stops, and begins to contract, leading to a big crunch scenario where all matter collapses back into a singularity, and from that singularity, another Big Bang could occur, leading to a new cycle. This idea, while still largely theoretical, raises intriguing questions about the nature of time and whether time itself is something that began with our universe or whether it has always existed in some form. Another noteworthy concept is the ekpyrotic universe model, which posits that our universe is the result of a collision between two three-dimensional worlds or branes in a higher dimensional space. In this view, the Big Bang is not the beginning of everything, but rather a transition point from one state to another, suggesting that there was a pre-existing condition before our universe came into being, challenging our traditional understanding of time as a linear progression. The ekpyrotic model offers a framework where time might exist even before the Big Bang, though it would be fundamentally different from our current experience of time. Additionally, some physicists explore the idea of a quantum foam structure of space-time, where at extremely small scales, traditional concepts of time and space break down. In this view, time may not have a clear beginning or end, but rather exists in a fluctuating state, influenced by quantum mechanics. This challenges the notion of a singular beginning point and suggests a more complex tapestry of existence that includes multiple dimensions and states of reality. The implications of such theories can lead to profound philosophical questions about the nature of existence itself. Moreover, the no-boundary proposal, formulated by physicists Stephen Hawking and James Hartle, suggests that the universe does not have boundaries in the way we typically understand them. In this model, the universe is self-contained and does not require a starting point in time, implying that time as we know it may not exist in the traditional sense before the Big Bang. Instead, time could be a construct that emerges from a more fundamental state of reality, where the concept of a singularity is fascinating as it is deeply intertwined with the ideas of time and the Big Bang, which marks the beginning of our universe, where the ideas of a singularity in the context of physics and cosmology refers to a point where certain quantities like density and temperature become infinite. This idea is often associated with black holes, but it also plays a crucial role in our understanding of the universe's origin. We talk about the Big Bang, we're describing a moment approximately 13.8 billion years ago when the universe expanded from an extremely hot and dense state. At this moment, before the expansion could even begin, all the matter and energy of the universe were concentrated at a single point, which we consider a singularity. Now, this singularity challenges our traditional understanding of time. In classical physics, time is viewed as a constant, flowing steadily from the past into the future. However, at the moment of the Big Bang, time itself is believed to have begun. This means that prior to the Big Bang, the concept of time as we know it may not have existed. This idea is both perplexing and exciting, as it suggests that the universe, as we understand it, has a beginning, and that time is not an eternal backdrop, but rather something that emerged with the universe itself. As we delve deeper into the implications of singularities, we must also consider how they relate to our understanding of the universe's evolution. After the initial singularity of the Big Bang, the universe underwent rapid expansion, a phase known as cosmic inflation, where space itself expanded faster than the speed of light. During this period, time began to take shape in a more familiar way, allowing for the formation of particles, atoms, stars, and galaxies. This expansion from the singularity led to the universe we see today, filled with a complex web of structures and phenomena. The mathematics that describes these singularities, particularly in Einstein's general relativity, suggests that space and time are interconnected in ways that challenge our intuition. The theory implies that extreme gravitational forces, like those found in black holes or at the moment of the Big Bang, can warp the fabric of space-time, leading to the breakdown of our conventional understanding of time. As we approach a singularity, the equations predict that time may behave differently, raising intriguing questions about the nature of reality itself. Moreover, scientists are still trying to reconcile the concept of singularities with quantum mechanics, which governs entropy, a concept often associated with disorder and randomness. Plays a fascinating role in discussions about time, particularly in the context of the Big Bang, which marks the beginning of our universe. In thermodynamics, entropy measures the amount of energy in a physical system that is no longer available to do work, and it tends to increase in isolated systems over time, a principle known as the second law of thermodynamics. When we turn our attention to the moments leading up to the Big Bang, or even the idea of time itself before that event, we encounter some intriguing complexities. According to the prevailing theories in cosmology, the Big Bang represents not just the birth of matter and energy, but also the origin of space and time as we understand it. If we consider the universe at its earliest moments, when it was extremely hot and dense, we can think of it as having very low entropy. This seems counterintuitive, as we often associate low entropy with order and high entropy with chaos. But in this case, the state of the universe was highly ordered, with all matter and energy concentrated in a singularity. As the universe expanded, entropy began to increase, leading to the formation of stars, galaxies, and eventually planets. This rise in entropy is tied to the arrow of time, giving us a directionality that we observe in our universe today. So when we ask about the role of entropy in discussions about time before the Big Bang, we step into a realm of speculation and theoretical physics, since our conventional understanding of time and causality breaks down at that singular point. Some scientists suggest that if time existed before the Big Bang, it might have been characterized by a different set of physical laws, and thus the usual concept of entropy might not apply in the same way. There are hypotheses, such as the cyclical model of the universe, which propose that the universe undergoes endless cycles of expansion and contraction. In such models, the entropy would reset at the beginning of each cycle, allowing for a new low entropy state, which raises provocative questions about the nature of time itself. Moreover, some physicists, including Stephen Hawking, explored the idea that the universe could potentially be finite yet unbounded, meaning that time might not have a traditional beginning or end. This perspective reshapes our understanding of entropy in relation to time, suggesting that what we perceive as time might be a feature of our universe's structure rather than a universal trait applicable at all. The concept of time before the Big Bang is a fascinating topic, one that has intrigued scientists, philosophers, and thinkers across cultures for centuries. In the realm of physics, many scientists suggest that time, as we understand it, began with the Big Bang itself, about 13.8 billion years ago. This idea challenges our common perceptions of time, which often see it as linear and continuous. However, various cultures and philosophies provide unique perspectives on time, offering a rich tapestry of interpretations. In ancient Hindu philosophy, time is often viewed as cyclical rather than linear. The concept of Kalachakra, or the Wheel of Time, illustrates this idea, where time is seen as a repeating cycle of creation, preservation, and destruction. In this view, the universe goes through endless cycles of birth and rebirth, suggesting that the notion of before the Big Bang might not hold the same significance, since time itself is part of a larger eternal cycle. Similarly, ancient Greek philosophers like Heraclitus proposed that everything is in a constant state of flux, emphasizing change over permanence. In contrast, Parmenides argued that change is an illusion and that true reality is timeless. These differing views reflect a philosophical tension about the nature of time itself, and whether it is a fundamental aspect of the universe or merely a human construct. Many Indigenous cultures, time is often perceived as something deeply connected to nature and the cycles of life. For example, the Native American concept of two-spirit embraces the idea that time is not just a linear progression, but rather a series of interconnected moments that reflect the relationship between the past, present, and future. In this understanding, the universe is alive with stories and experiences that transcend conventional timelines, suggesting that concepts of creation and existence may not be bound by our scientific definitions. Similarly, in East Asian philosophies, particularly in Taoism, time is viewed as an integral part of the natural flow of the universe. The Tao Te Ching teaches that time is not something to be controlled or mastered, but rather something to be embraced and understood as part of the greater harmony of existence. This perspective can shift the conversation about the Big Bang and time, suggesting that the origins of the universe, and indeed time itself, may be more about balance and interconnectedness than a single event. In the realm of modern scientific thought, physicists like Stephen Hawking and others have proposed models where time itself could emerge from more fundamental structures of reality. The no-boundary proposal, introduced by the renowned physicist Stephen Hawking, presents a fascinating concept in the realm of cosmology, particularly concerning the origins of the universe. This proposal suggests that the universe is finite but has no boundaries, meaning that, much like the surface of a sphere, it does not have edges or a distinct starting point, which challenges our traditional understanding of time and space. In this model, time behaves like a spatial dimension when we approach the beginning of the universe, which is described as a singularity. Instead of encountering a point in time where the universe began, the no-boundary proposal posits that we simply encounter a smooth, rounded geometry where time transitions into space. Hawking, along with his colleague James Hartle, developed this idea as a solution to the puzzle of what happened before the Big Bang. According to their theory, if one were to trace the timeline of the universe back to its origins, they would find themselves in a realm where conventional rules of time as we know them cease to apply. In this scenario, the universe can be described without the need for initial conditions, making it possible for the universe to spontaneously arise from nothing, without a definitive cause or event that marks its inception. This leads to the conclusion that our understanding of time, particularly in the context of the universe's beginning, is more complex than we might assume. The implications of the no-boundary proposal extend beyond the birth of the universe. It invites us to rethink the nature of time itself. Instead of viewing time as a linear progression from past to present to future, it invites a more nuanced perspective, where time may be more like a dimension that can loop back on itself, allowing for a seamless continuity that connects all moments in a way that defies our everyday experiences. This perspective resonates with certain interpretations in quantum mechanics, where the behavior of particles does not always align with our classical understanding of time, suggesting that the universe operates under rules that we are still striving to fully comprehend. Furthermore, the no-boundary proposal also touches on the concept of the multiverse, proposing that our universe is just one of many, each potentially having its own set of laws and dimensions. This idea expands the horizon of our understanding, suggesting that what we perceive as our singular reality could be part of a vast and intricate tapestry of universes, each with its own history, timeline, and characteristics. As we continue to explore these profound questions, the no-boundary proposal remains a cornerstone in the quest to understand the peace of the universe. The nature of time is a fascinating topic that invites us to explore complex theories and ideas, many of which challenge our everyday understanding of the universe. In our common experience, we perceive time as linear, moving from past to present and leading into the future. But when we delve into the realm of cosmology and theoretical physics, things become less straightforward. The Big Bang, which occurred about 13.8 billion years ago, marks what we often consider the beginning of our universe. But the question arises, what existed before that moment? And what was the nature of time itself? Some physicists propose that time as we know it might not have existed prior to the Big Bang, suggesting that the concept of before is meaningless in this context. According to Einstein's theory of relativity, time is intertwined with space, forming what we refer to as spacetime. In this framework, the Big Bang can be viewed not just as a point in time, but as the origin of space and time itself. Thus, asking what happened before the Big Bang may be akin to asking what is north of the North Pole, a question that doesn't have a meaningful answer within our current understanding. On the other hand, some theories suggest that time could be cyclical. This idea is rooted in certain interpretations of the universe's expansion and contraction, proposing that the universe could undergo infinite cycles of big bangs and big crunches. The cyclical model implies that time is not just a straight line, but rather a recurring loop, where the universe expands, eventually collapses back into a singularity, and then expands again. Such a perspective offers a different view on time, painting it as a series of cycles rather than a single, linear journey. Further complicating the concept of time before the Big Bang are theories from quantum mechanics. Some physicists suggest that time could exist in a form we do not yet understand, potentially existing in a state that is more complex than linear or cyclical. In this view, time could be seen as more of a multi-dimensional construct where different timelines or realities could coexist. This idea hints at a universe that is far richer and more intricate than our current models suggest, leading to possibilities that challenge our fundamental notions of reality. In addition to these scientific theories, philosophical discussions about the nature of time add another layer to this inquiry. Philosophers have long debated whether time is an objective reality or simply a human construct, a measure of change. Black holes, those mysterious regions of space-time where gravity is so strong that nothing, not even light, can escape, present some of the most profound challenges to our understanding of time, as they warp the very fabric of space-time itself. When we think about black holes, we often envision a dark void, but at their core lies a singularity, a point where the gravitational pull becomes infinite and the laws of physics as we know them start to break down. According to Einstein's theory of general relativity, as you approach a black hole, time itself begins to behave in strange ways, stretching and slowing down for an outside observer, while for someone falling into the black hole, time might feel normal, but they would face an overwhelming tidal force, ultimately leading to spaghettification. The famous thought experiment involving a black hole illustrates this phenomenon well. If an astronaut were to hover near the event horizon of a black hole, and a friend remained far away, the astronaut would experience time normally, while their friend would see time for the astronaut moving much slower. This effect is known as gravitational time dilation, and it arises because the intense gravity around the black hole warps space-time. As the astronaut nears the event horizon, they would witness the universe outside speeding up, observing galaxies and stars racing by, millions of years of cosmic evolution unfolding in moments, while their own clock ticked steadily. These ideas challenge our traditional notions of time, as they suggest that time is not a constant, universal experience, but rather something that can be influenced by gravity and velocity. The implications of this are staggering, as they raise questions about the nature of reality itself. How do we reconcile the experience of time for someone near a black hole with that of someone far away? This divergence poses difficulties for the concept of simultaneity in physics, which is critical for understanding how events are ordered in time. In addition to the warping of time near black holes, there's also the question of what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, But the singularity at the center of a black hole seems to challenge this principle. The so-called black hole information paradox arises from this conundrum, leading to intense debates among physicists about whether the lost information could somehow be preserved at the event horizon, or if it is truly lost forever, which would require a complete overhaul of our understanding of both quantum mechanics and general relativity. Furthermore, eternal inflation is a fascinating concept in cosmology, which suggests that the rapid expansion of the universe, known as inflation, did not just happen once, but is an ongoing process, happening in various regions of space at different times. According to this idea, while our observable universe underwent a brief period of exponential growth just after the Big Bang, other regions of the universe are still inflating, creating a vast multiverse of bubble universes, each potentially having different physical laws or constants. This theory suggests that inflation could create an infinite number of these bubble universes, each existing independently, and while our own universe is one of these bubbles that cooled and formed galaxies, stars, and planets, there could be countless others, still inflating, still forming. The concept of eternal inflation raises intriguing questions about time. Traditionally, the Big Bang is considered the beginning of time, as we understand it, because prior to this event, the universe was thought to be in an extremely hot and dense state. However, if eternal inflation is correct, then time might not have a clear starting point, as the process of inflation could extend infinitely into the past in various regions of the multiverse. In this view, our Big Bang represents just one moment in a much larger cosmic tapestry, where the fabric of reality is continuously woven through the ongoing inflation of other regions. Consequently, in regions where inflation is still occurring, time could be experienced differently. And the physical processes that lead to the formation of new universes might be happening simultaneously with our own universe's evolution. This means that time before the Big Bang, instead of being a void of nothingness, could be filled with an infinite number of events and processes occurring in other parts of the multiverse, leading to a rich and complex cosmic structure, one that challenges our intuitive understanding of time and causality. The implications of eternal inflation are profound, suggesting that our universe is just a small piece of an ever-expanding, ever-evolving cosmos, where the rules of time and space might not apply in the same way we experience them today. This theory, while still under exploration and subject to ongoing research, offers a compelling narrative about the origins of the universe, and it opens up exciting possibilities for understanding our place in a potentially infinite multiverse, where the nature of reality might be far more intricate than we can currently comprehend. As scientists continue to study cosmic microwave background radiation and gather evidence, scientists use mathematical models to theorize about time before the Big Bang by exploring the fundamental laws of physics, especially through the lens of general relativity and quantum mechanics. The Big Bang theory suggests that the universe has been expanding since it began, but when it comes to what happened before that moment, things get quite complex. The mathematical framework allows scientists to simulate various conditions of the early universe, and also to probe the nature of space-time itself. One approach that scientists use involves examining singularities, which are points in space where the laws of physics as we know them break down, such as the singularity at the center of a black hole. By employing advanced mathematical tools, they can create models that describe how space-time might behave near these singularities and whether time itself can exist in a meaningful way before the Big Bang. Some models suggest that time as we know it could have originated from a different state of the universe, such as from a prior contracting universe, a concept known as the cyclic model. Another avenue involves the use of string theory, where scientists propose that the fundamental building blocks of the universe are not particles, but rather tiny strings. In this framework, they can create mathematical scenarios that allow for the existence of multiple dimensions, and propose that our universe could be one of many existing within a vast multiverse. This opens up the possibility of understanding time and space in ways that traditional models cannot, as it suggests that the Big Bang might not be the absolute beginning, but rather a transition from one state to another. Moreover, researchers are investigating cosmological inflation, a theory that suggests a rapid expansion of the universe occurred just after the Big Bang. By using mathematical equations, they can model how such inflation could have laid the groundwork for our current universe and possibly hint at what might have existed beforehand. These models can incorporate quantum fluctuations, which are random variations at a very small scale, and these fluctuations could have played a significant role in the formation of the universe, even before the Big Bang occurred. In addition to these theoretical considerations, scientists often rely on observational data, such as cosmic microwave background radiation, to refine their models. By analyzing the patterns and anomalies in this radiation, they can test their mathematical predictions against what we observe in the universe today. This interplay between mathematics and observation allows for a more comprehensive understanding of the universe's origins and the nature of time itself. Through all these methods, mathematical modeling serves as a bridge between abstract concepts and the physical universe, helping scientists. The question of whether there are observable phenomena today that can give us clues about the time before the Big Bang is a fascinating and complex one, and it taps into the very heart of cosmology and our understanding of the universe. While the Big Bang is often described as the starting point of our universe, the concept of time before the Big Bang is still a subject of much debate among physicists and cosmologists. One of the key ideas comes from the study of cosmic background radiation, which is the afterglow of the Big Bang, a faint microwave radiation that fills the universe, and it provides a snapshot of the universe when it was just about 3,800,000 years old. Scientists use this radiation to learn about the conditions of the early universe, but it does not directly tell us what happened before that moment. However, some theories, such as those involving inflation, suggest that the universe underwent a rapid expansion that could have occurred before the Big Bang as we know it, although this remains speculative and difficult to observe directly. Another intriguing phenomenon is the detection of gravitational waves, which are ripples in space-time caused by massive events, like the merging of black holes or neutron stars. These waves provide a new way to observe the universe and could potentially offer insights into the conditions of the early universe and any events that happened before the Big Bang, especially if there were primordial gravitational waves generated during an earlier phase of cosmic evolution. Furthermore, researchers are investigating quantum gravity theories, which attempt to unify general relativity and quantum mechanics, and some of these theories suggest that time itself might behave differently on very small scales or at extreme energies. Some scientists propose models like the cyclic universe theory, which suggests that the universe undergoes infinite cycles of expansion and contraction, meaning that what we perceive as the Big Bang could be just one phase in a much larger, ongoing process. If this is true, then evidence from cosmic phenomena, such as the distribution of galaxies and cosmic microwave background fluctuations, might hint at previous cycles. Additionally, while direct observation of phenomena before the Big Bang remains elusive, the study of dark matter and dark energy also plays a critical role in understanding the universe's evolution, as these mysterious components make up most of the universe's total energy density and could provide indirect clues about the early universe and what may have preceded it. Moreover, some researchers are exploring the concept of quantum foam, which postulates that at the very smallest scales, space-time could be subject to quantum fluctuations. The concept of multiple universes, often referred to as multiverse theory, opens up fascinating possibilities for understanding time, and it challenges our traditional perceptions in intriguing ways. The multiverse theory suggests that our universe is just one of many, possibly an infinite number of universes, each with its own distinct laws of physics, constants, and histories, physics and prosperity. This idea stems from various interpretations of quantum mechanics, particularly the many worlds interpretation. which posits that every quantum event spawns a branching of realities, creating parallel universes. In this context, time may not be a linear progression, as we commonly perceive it, but rather a complex and richly woven tapestry, where every decision and event could lead to divergent timelines. In a multiverse scenario, the nature of time might also vary between universes, which means that what we understand as the flow of time could be entirely different elsewhere. For instance, in some universes, time could run faster or slower than our own, or it might loop or even be cyclical. This variance allows for a broader understanding of temporal dimensions, as time could manifest differently based on the physical laws governing each universe. For example, in one universe, time might appear to have a beginning and an end, while in another, time could be infinite and eternal, without a defined starting point or conclusion. Moreover, the multiverse theory raises thought-provoking questions about the nature of causality and how events unfold. If there are countless versions of events happening across different universes, this implies that every possible outcome of a decision exists in some form. This leads to a rethinking of how we view choices and consequences, suggesting that every moment could branch off into its own reality, with its own timeline, creating a web of interconnected existences. This multifaceted approach to time allows us to consider that our understanding of past, present, and future is just one perspective among many, and there could be countless other versions of our past and future playing out in parallel realities. Furthermore, if time is not a singular experience, but rather a multitude of experiences across various universes, it complicates our understanding of concepts like fate and destiny. In a multiverse framework, the paths that lie ahead are not predetermined, but rather a series of possibilities influenced by choices made in countless other timelines. This perspective suggests that what we perceive as a linear journey through time might just be one of many paths, shaped by the infinite potential of the multiverse. In summary, the influence of multiverse theory, Planck time, which is approximately 5.39 times 10 to the negative 44 seconds, holds a special place in the study of the universe's origins, serving as the smallest measurable unit of time, beyond which our current understanding of physics begins to break down. This minuscule time frame is derived from fundamental constants, including the speed of light, the gravitational constant, and Planck's constant, and it represents a point in time after the Big Bang, when the universe was incredibly hot and dense. In the context of the universe's origins, the significance of Planck time lies in its role as a boundary for our understanding of the early universe, where conventional physics, as described by Einstein's theories of relativity and quantum mechanics, begins to merge into a single framework which scientists refer to as quantum gravity. This merging is essential for comprehending what might have transpired during the earliest moments of the universe, as conditions were so extreme that our existing theories cannot accurately describe them. During the Planck time, it is theorized that the very fabric of space-time was undergoing rapid fluctuations, leading to a chaotic environment where particles and forces were not yet separated as they are in our current universe. Understanding this era could unlock the mysteries of how the universe expanded and cooled, allowing matter to form, which eventually led to the stars, galaxies, and planets we see today. Some physicists posit that the universe's fate, as well as its initial conditions, could be significantly influenced by phenomena occurring during this brief time span. Furthermore, Planck time serves as a crucial reference point for theories of cosmology, particularly in models that explore the nature of the Big Bang and the subsequent inflationary period, during which the universe experienced exponential growth. In essence, Planck time represents a frontier in theoretical physics, where scientists strive to formulate a coherent picture of the universe's birth. And it challenges our understanding of time and space, urging researchers to seek a deeper theory that can bridge general relativity with quantum mechanics. This quest not only enriches our comprehension of the cosmos, but also invites profound questions about the nature of reality itself and how time, as we understand it, began its journey along with the universe. As we delve deeper into this enigmatic phase, we may eventually uncover insights that reshape our understanding of existence, pushing the boundaries of science and philosophy alike. The concept of time as we understand it today becomes quite complex when we try to consider what existed before the Big Bang, an event that is thought to have occurred around 13.8 billion years ago, marking the beginning of our universe, with all its matter, energy, space, and importantly, time itself. According to the prevailing theories in cosmology, time is intrinsically linked to the fabric of the universe and its expansion. Prior to the Big Bang, the universe was compressed into an incredibly hot and dense state, often referred to as a singularity, where the laws of physics, as we know them, break down. In this context, it becomes difficult, if not impossible, to measure or define time in a meaningful way, because time, in our current understanding, requires a framework of space and causality which did not exist before the Big Bang. One way to look at this is to consider how we measure time. We typically rely on events in the sequence in which they occur, using clocks and other instruments that depend on physical processes like the oscillation of atoms or the rotation of the Earth. However, without a universe to contain these processes, the very concept of before loses its meaning, as any notion of time would collapse into a singularity. Some physicists and cosmologists suggest that time itself may have emerged from the conditions of the Big Bang, and therefore asking what happened before it might be akin to asking what is north of the North Pole, a question that doesn't hold meaning within our current understanding of spatial dimensions. In theoretical frameworks, like those involving quantum gravity or string theory, some researchers propose models where time can be treated differently, possibly existing in a more abstract form before the Big Bang. These models are speculative, and while they attempt to provide insights into the nature of time and the universe, they remain unproven and are still the subject of intense debate among physicists. Additionally, some theories suggest that there could be multiple universes, or a multiverse, where our universe is just one bubble among many, and in this context, time might be relative, varying from one universe to another, further complicating the idea of measuring time before our own universe came into existence. Ultimately, the question of whether time can be measured or defined in a meaningful way before the Big Bang leads us into the realm of philosophy as much as it does physics, challenging the limits of human understanding and the nature of existence itself. The scientific community's view on time before the Big Bang has undergone significant evolution, marked by a transition from philosophical speculation to a more grounded scientific inquiry. Initially, the concept of time itself was deeply intertwined with the notion of the Big Bang, which many physicists, including the renowned Albert Einstein, viewed as the origin of not just matter and energy, but also of space and time. In the early 20th century, the prevailing belief was that time began with the Big Bang, meaning that asking what happened before it was often seen as a nonsensical question, similar to asking what is north of the North Pole. However, as theories in cosmology advanced, particularly with the development of quantum mechanics and general relativity, the understanding of what constitutes time began to take on new dimensions. By the late 20th century, some physicists began to explore the idea of a multiverse, suggesting that our universe, with its own Big Bang, might be just one of many universes, each with its own timeline. This perspective opened the door to discussions about a sort of time that could exist outside of our own universe, a realm where the traditional understanding of time might not apply in the same way. In particular, the work of cosmologists like Alan Guth, who developed the inflationary model of the universe, provided a framework suggesting that the universe went through a rapid expansion shortly after the Big Bang, which further complicated the concept of time leading up to that event. As research progressed, ideas such as loop quantum gravity emerged, proposing that space and time are quantized, leading to the possibility that time might not have a singular beginning or end, but rather could be part of a cyclic process, where universes are born and die in an ongoing cycle. This concept challenges the older view of a linear timeline, suggesting instead that time could be more complex, possibly looping back on itself in ways that we do not yet fully understand. The introduction of theories like the ekpyrotic model, which posits that our universe could have resulted from the collision of two three-dimensional worlds in a higher dimensional space, added even more layers to the discussion, suggesting that time could have existed in some form before the Big Bang. In recent years, advanced observational tools such as the Hubble Space Telescope and the emerging James Webb Space Telescope have provided new data about the early universe, allowing scientists to probe deeper into the conditions that existed just after the Big Bang. This has led to the concept of a universe without a beginning opens up a fascinating realm of philosophical implications, particularly when we consider the nature of time itself. Traditionally, many philosophical and scientific frameworks have assumed that time is linear, progressing from a definite starting point to an end point, much like an arrow flying through space. However, if the universe has no beginning, this linear perspective on time is challenged significantly. Philosophers like Immanuel Kant have argued that time is not an absolute entity, but rather a framework through which we perceive events and existence. In a universe without a beginning, time could be perceived as cyclical or even as an infinite continuum where past, present, and future are not strictly demarcated but instead exist simultaneously in a kind of eternal recurrence. This raises questions about causality, which is the relationship between cause and effect that we often take for granted. If the universe is eternal, what does it mean for the cause of the universe itself? In classical physics, every effect has a cause, but in an infinite universe, one might argue that there could be an absence of a singular cause, leading to the existence of everything we observe. This could lead to a reinterpretation of the Big Bang theory, which posits a beginning point for our universe, suggesting instead that it might be just one phase in an eternal cycle of expansion and contraction, or perhaps even a part of a multiverse where different universes are birthed and extinguished in an endless process. Moreover, if time is infinite, it challenges our understanding of mortality and the significance of human life. Existentialist philosophers like Jean-Paul Sartre have tackled the implications of our existence within a finite timeline, but in an infinite temporal landscape, the weight of our choices and the meaning we assign to our lives could take on a different hue. If time stretches infinitely in both directions, does that render our individual experiences more or less significant? Does an infinite timeline diminish the importance of our actions, or does it enhance it by placing it within a broader context of existence that transcends our immediate comprehension? Additionally, the idea of an unending universe can lead to intriguing considerations about the nature of reality itself. If the universe is eternal, it might imply that every possible event or state of affairs has occurred or will occur at some point in the vast tapestry of time. This could suggest a form of determinism where all events are predestined to happen, or it may lead to a more complex understanding of free will, where our choices theories of quantum gravity, which aim to unify general relativity and quantum mechanics, are fascinating in their attempts to address the nature of time and the events surrounding the Big Bang. In classical physics, general relativity describes gravity as the curvature of space-time, meaning that time and space are intertwined, while quantum mechanics deals with the subatomic realm, where particles behave in unpredictable ways. When we discuss the Big Bang, we are talking about the very beginning of the universe, where our current understanding of physics seems to break down. This is where quantum gravity theories like string theory and loop quantum gravity come into play. String theory proposes that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar 3 dimensions of space and 1 of time. One intriguing aspect of string theory is its implication for time itself. Some models suggest that time could emerge from deeper, timeless phenomena. This means that rather than being a fundamental aspect of the universe, time could be a byproduct of the interactions of these strings, which could change our understanding of what happened at the very instant of the Big Bang. On the other hand, loop quantum gravity takes a different approach, positing that space itself is quantized, meaning it has a discrete structure at the smallest scales. In this framework, time and space can behave differently than we expect. Loop quantum gravity suggests that the Big Bang may not be the singular beginning of time, but rather a transition from a previous state, such as a contracting universe, leading into the expansion we observe today. This could imply that time, as we know it, might have different properties and behaviors at the quantum level, potentially allowing for a more fluid understanding of time across the cosmos. Both theories face significant challenges, particularly in how they account for the conditions at the singularity of the Big Bang, where densities and temperatures become infinitely high. The reconciliation of time with the events leading up to and following the Big Bang is still a puzzle. Researchers are exploring concepts like the idea of a pre-Big Bang scenario, where time itself could behave differently, and the universe might cycle through phases of expansion and contraction, blurring the lines of causality and chronological order. Additionally, the relationship between time and entropy, which is a measure of disorder, plays a critical role in these theories. The second law of thermodynamics states that entropy tends to increase over time, leading to the conclusion that observational evidence plays a crucial role in shaping theories about the universe, particularly when it comes to understanding time before the Big Bang, a concept that challenges our conventional understanding of time and space. When scientists think about the moments leading up to the Big Bang, they often rely on the cosmic microwave background radiation, which is a faint glow left over from the hot, dense state of the early universe. This radiation, discovered in the 1960s, provides a snapshot of the universe approximately 3.80000 years after the Big Bang, allowing researchers to infer a great deal about the conditions that existed at that time. However, when we talk about the moment of the Big Bang itself, things become more complicated, as our current understanding of physics, particularly general relativity, suggests that time as we know it might not have existed before the Big Bang. This leads scientists to explore theories like the concept of a multiverse, where our universe is just one of many, each with its own set of physical laws and timelines. The idea is that if there are other universes, there could be different forms of time, or even instances where time behaves differently, which raises fascinating questions about what came before our own universe. Another significant piece of observational evidence comes from the study of cosmic inflation, a theory that suggests the universe underwent a rapid expansion just after the Big Bang. This expansion would have smoothed out the universe, leading to the distribution of galaxies and cosmic structures we observe today. By studying the patterns and fluctuations in the cosmic microwave background, scientists can gather clues about the inflationary period, and some researchers even propose that these fluctuations could hint at pre-Big Bang conditions. Additionally, researchers are delving into the realm of quantum mechanics, exploring how the uncertainty principle might affect our understanding of time and space at very small scales. Some theories, like loop quantum gravity, suggest that space and time may be quantized, leading to the idea that time could be cyclic, potentially allowing for a universe that expands and contracts rather than a singular beginning. Such theories are still under development, but they underscore the importance of observational evidence in shaping our understanding of the universe's origins. Furthermore, astrophysicists are studying black holes, which are regions of space-time where gravity is so strong that nothing, not even light, can escape. The behavior of matter and energy near black holes could provide insights into the nature of time itself, particularly as black holes are thought to warp space-time in extreme ways. This, when we delve into the concept of causality in relation to the time before the Big Bang, we enter a realm of profound and complex ideas that challenge our usual understanding of cause and effect. In everyday life, we see causality as a straightforward chain of events where one thing leads to another and time flows in a linear manner. However, when we explore the universe's origins, particularly before the moment of the Big Bang, this familiar notion begins to unravel. The Big Bang is typically understood as the starting point of our universe, marking the beginning of time and space as we know them. So when we ponder what existed before this moment, we are confronted with questions that stretch the limits of our comprehension. In traditional physics, causality is closely tied to time. Events occur in a specific order, and a cause must precede its effect. However, if we consider the time before the Big Bang, we encounter theories that suggest time itself may not have existed in a form we can understand. Some physicists propose that the universe underwent a series of phases, including a potential contraction before the Big Bang, which could imply that what we perceive as time may have originated with the Big Bang itself. In such scenarios, the conventional cause and effect relationships we rely on may not apply, as there would be no before in the temporal sense, making it challenging to discuss causality in the usual way. Moreover, quantum mechanics introduces fascinating ideas that further complicate our understanding of causality. In the quantum realm, events can appear to be non-linear, and particles can be entangled in ways that defy classical notions of causation. This has led some theorists to suggest that the physics governing the universe before the Big Bang could also be governed by quantum principles, where causality might not follow the linear path we expect. Some models, like the cyclic universe theory, propose that the universe undergoes endless cycles of expansion and contraction, which raises questions about the nature of time itself and whether it can truly be said to have a beginning or an end. Additionally, the concept of a multiverse has emerged in some discussions about the time before the Big Bang. If multiple universes exist, each with its own set of physical laws, then causality might be vastly different in those realms compared to our own universe. In such a framework, events in one universe could potentially influence another in ways that challenge our conventional understanding of cause and effect. The implications are staggering, suggesting that causality, time dilation, and relativity introduce fascinating complexity to our understanding of time's origins, transforming what we think we know about the very fabric of the universe. According to Einstein's theory of relativity, time is not a constant, but rather it can stretch or compress depending on relative speeds and gravitational fields. This means that two observers traveling at different speeds or situated in different gravitational environments may experience time differently, leading to what we call time dilation. For example, a clock on a spaceship traveling close to the speed of light will tick more slowly compared to a clock on Earth, which raises intriguing questions about the nature of time itself. As we delve deeper into the implications of relativity, we begin to see that time is intrinsically linked to space, forming a four-dimensional continuum known as space-time. This relationship challenges the traditional view of time as a linear progression from past to future. Instead, time becomes a flexible dimension, affected by the mass of objects and their velocities. For instance, near a black hole, where gravity is incredibly strong, time moves at a significantly slower rate compared to regions with weaker gravitational pull. This phenomenon complicates our understanding of time's origins, as it suggests that the flow of time could be influenced not only by the initial conditions of the universe, but also by the gravitational fields and velocities of the objects within it. Furthermore, the concept of simultaneity, which is the idea that two events occurring at the same time for one observer may not be simultaneous for another, adds another layer of complexity. This idea challenges our intuitive grasp of time, suggesting that there There's no absolute time shared by all observers. Instead, time becomes relative, depending on motion and gravity. This relativity of simultaneity can lead to paradoxes and dilemmas, especially in thought experiments involving faster-than-light travel or interactions between objects at significant distances. Looking at the origins of time, the Big Bang theory provides a fascinating backdrop. It posits that time itself began with the Big Bang approximately 13.8 billion years ago, marking the birth of the universe and the unfolding of space and time. However, as we consider the effects of time dilation and relativity, we are confronted with questions about what happened before the Big Bang, or even if before has any meaning in a universe where time itself emerged from this cataclysmic event. Some theoretical models suggest that time may be cyclical, or that it could have different properties in other parts of the concept of time before the Big Bang opens up a fascinating realm of metaphysical questions, as it challenges our understanding of existence, causality, and the very fabric of the universe. Traditionally, we perceive time as a linear progression, marked by past, present, and future, with events unfolding in a sequence. However, if we consider the Big Bang as the origin of our universe, we are left to ponder what, if anything, existed prior to this monumental event. Did time itself begin at the moment of the Big Bang, or was it merely a transformation of an already existing state? This question leads us into deep philosophical inquiries about the nature of time itself. Some theorists suggest that time is a construct of the universe, intimately tied to space, matter, and energy. If this is true, then it raises profound questions about the nature of reality before the Big Bang. Was there a timeless realm where traditional notions of cause and effect did not apply? Did events exist in some form? Or was there simply a void, a state of nothingness, where conventional time had no meaning? These questions evoke thoughts of metaphysical concepts, such as infinity and eternity, which can feel abstract and elusive. Moreover, the idea of a universe before the Big Bang introduces the possibility of alternate dimensions or realities. Could time be cyclical, with universes collapsing and rebirthing in a cosmic cycle, suggesting that our universe is just one chapter in an endless series of cosmic stories? This notion invites us to explore the implications of a multiverse, where each universe could possess different laws of physics, time, and existence. The implications extend to the nature of causality itself. If we accept that the Big Bang was the beginning of our universe, then we must grapple with questions surrounding the cause of the Big Bang. Is there a cause beyond our universe? And if so, what does that mean for our understanding of existence? Some philosophers argue that every effect must have a cause, but if time did not exist before the Big Bang, can we even apply our usual understanding of causality? This leads to the exploration of the concept of the now. If time is an emergent property of the universe, what does it mean for the experience of the present moment? Philosophers like Immanuel Kant argue that time is a fundamental framework to which we perceive reality. But if time began with the Big Bang, then how do we reconcile our experience of the present with a universe that the question of time before the Big Bang is a fascinating topic that has intrigued the concept of time from different perspectives. In physics, time is often considered a fundamental dimension, woven into the fabric of space-time itself, as described by Einstein's theory of relativity. According to this framework, time began with the Big Bang, which marks the beginning of our universe, and thus the concept of before becomes tricky, if not meaningless, since time as we understand it did not exist prior to that moment. Some physicists, however, delve into speculative theories that suggest time could be cyclical, or that our universe might be part of a larger multiverse where different universes experience their own timelines, potentially allowing for a kind of before in some other context. On the other hand, cosmology, which is the study of the universe's origins and evolution, grapples with the implications of the Big Bang and how it relates to the concept of time. Cosmologists use mathematical models, such as those derived from general relativity, to explore the universe's expansion and its beginnings. In this field, some suggest that the universe could have gone through various phases, possibly even existing in a quantum state before the Big Bang, where traditional notions of time and space are not applicable. Theories like quantum gravity or string theory propose that the universe could have undergone a series of contractions and expansions, hinting at a more complex temporal structure than the linear progression we typically associate with time. Philosophy, meanwhile, offers a different lens through which to view time. Philosophers ponder the nature of time, questioning whether it is absolute or relational, and how it relates to existence itself. The question of time before the Big Bang invites deep philosophical inquiry into the meaning of before, when there was no time as we understand it. Some philosophers argue that if time began with the Big Bang, then asking what happened before it may be akin to asking what lies north of the North Pole, a question that defies conventional understanding. Others explore the implications of eternalism, the idea that past, present, and future are equally real, which could suggest that while our universe has a defined starting point, the concept of time itself may extend beyond our universe's boundaries. Together, these scientific disciplines weave a rich tapestry of ideas and theories, each contributing unique perspectives on the enigmatic question of time before the Big Bang. And while the answers remain, the cosmic microwave background radiation, often abbreviated as CMB, plays a crucial role in our understanding of the early universe. Acting as a relic from the time just after the Big Bang, around 38,000,000 years post-event, when the universe cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. Before this moment, the universe was a hot, dense soup of particles, photons, and radiation, which were unable to travel freely because of the constant scattering off charged particles, creating a foggy state where light couldn't escape. However, as the universe expanded and cooled, when the temperature dropped to about 3,000 Kelvin, photons could finally decouple from matter, allowing them to travel vast distances. And this moment is what we call recombination. The CMB is essentially the afterglow of that moment, now cooled to just 2.7 Kelvin, permeating the entire universe. It is almost uniform, but it contains tiny fluctuations which are fundamental because these variations represent the seeds of all future structure, such as galaxies and galaxy clusters, that would form later in the universe's evolution. By studying these fluctuations, scientists can glean information about the density, composition, and expansion rate of the universe, leading to insights into its overall geometry and fate. Additionally, the CMB offers a snapshot of the universe when it was just a baby, providing a wealth of information about its early conditions, including the density of baryonic matter, dark matter, and dark energy, illuminating the fundamental processes that governed the development of the cosmos. The analysis of the CMB has led to the establishment of the lambda cold dark matter model, or LCDM, which is the prevailing cosmological model explaining the universe's evolution and structure. Moreover, the CMB has been instrumental in confirming the Big Bang theory, as it provides a consistent framework that aligns with the predictions made by this model. The precise measurements of the CMB's temperature fluctuations, particularly from missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite, have allowed scientists to refine their understanding of various cosmological parameters, such as the Hubble constant, which describes the rate of expansion of the universe, and the density of various components like dark energy, which dominates the universe's energy budget. A study of the CMB also sheds light on the universe's overall geometry, revealing it to be flat, with only a slight margin of error, which the concept of a beginning, often associated with the Big Bang theory, suggests that the universe had a specific point in time when it started to exist, which aligns with our traditional understanding of beginnings, where something comes into being from nothing. However, certain interpretations of quantum mechanics challenge this notion, presenting a more complex view of reality. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, introduces ideas that defy classical intuition, such as superposition and entanglement. And, in some interpretations, it leads to scenarios where the universe might not require a clear-cut beginning. For instance, the concept of quantum fluctuations suggests that particles can spontaneously emerge from a vacuum state, seemingly creating something from nothing, which complicates the traditional narrative of a singular starting point for the universe. Moreover, some interpretations of quantum mechanics, like the many worlds interpretation, propose that every quantum event branches into multiple realities. Time occurs in its own separate universe, leading to questions about what it truly means to have a beginning, and whether that concept even applies when there are potentially infinite outcomes coexisting. In this view, the universe may not have a single origin, but rather a vast web of possibilities, where each beginning is just one of many outcomes unfolding in a larger multiverse. Additionally, the nature of time itself, as examined in quantum mechanics, further blurs the lines of how we perceive beginnings and endings. In general relativity, time is interwoven with space and can be influenced by gravity, suggesting that time itself may not be a constant, unchanging backdrop, but rather a dynamic, flexible dimension. This leads to intriguing implications, as certain models of time in quantum mechanics propose that time could be emergent, arising from more fundamental processes, rather than a linear progression that strictly defines when events start and finish. Consequently, when we try to reconcile these scientific concepts with our understanding of a beginning, we may find ourselves grappling with the idea that beginnings might not exist in the way we traditionally think, or that they could manifest differently in various contexts. Furthermore, the philosophical implications of these interpretations raise more questions than answers, as they challenge our understanding of causality and existence, leading to discussions about the meaning of reality itself. In this light, the interplay between quantum mechanics and our perception of beginnings encourages a re-evaluation of how we understand the universe, pushing us to consider that the origins of reality could be communicating the concept of time before the Big Bang poses significant challenges, primarily because our understanding of time is deeply rooted in our everyday experiences, which are not equipped to handle the complexities of cosmological theories. First, it's essential to recognize that, according to current scientific understanding, the Big Bang marks not only the beginning of space, but also the beginning of time itself. So, talking about before the Big Bang can be profoundly confusing. Most people perceive time as linear, a sequence of events that can be measured and quantified, but when we delve into the realm of the universe's origins, we encounter a situation where those familiar concepts begin to break down. The idea that time may not have existed prior to the Big Bang challenges our basic intuitions, leading to potential misunderstandings, as it suggests that there was no before in the way we typically understand it, making it difficult for the general public to grasp what that truly means. Furthermore, scientific terminology can often alienate those not versed in physics or cosmology, as concepts like singularities, quantum fluctuations, and space-time can feel abstract and esoteric, creating barriers to comprehension. It is also crucial to convey that our current scientific models, like the theory of relativity and quantum mechanics, are still evolving, which can lead to uncertainty about what we know or think we know about the universe's beginnings. This uncertainty can make it hard to present a clear narrative, for the concept of time before the Big Bang is not just a simple explanation, but an area of active research and debate among physicists. Additionally, metaphysical implications arise, as people often carry philosophical beliefs about time and existence, and reconciling these with scientific views can create cognitive dissonance. Many might wonder if time is a fundamental aspect of the universe or merely a construct of human perception, and conveying these ideas requires delicate balance between scientific rigor and accessible language. On top of that, visualizing concepts related to the Big Bang, such as the expansion of the universe or the idea of singularity, can be difficult, as these are not phenomena we can directly observe or experience in our daily lives. Engaging storytelling, analogies, and relatable examples can help bridge this gap. Yet finding the right comparisons that resonate with a diverse audience remains a formidable task. Lastly, there's the challenge of competing narratives. Popular media often dramatizes or oversimplifies complex scientific ideas, which can lead to misconceptions, making it difficult for accurate information in the fascinating realm of theoretical physics. The discussion around hypothetical particles and fields, such as the inflaton, often leads us to ponder the intricate nature of time itself, which is the fundamental aspect of our universe. The inflaton is a proposed field believed to drive cosmic inflation, a rapid expansion of space that occurred just after the Big Bang, and its implications extend beyond mere expansion, hinting at deeper connections with time. To understand this relationship, we must first consider how inflation affects the structure of the universe, as during this brief yet incredibly significant period, the inflaton field would have caused the fabric of space-time to stretch exponentially, influencing the distribution of matter and radiation we observe today. When we think about time in the context of the inflaton, we delve into the concept of how events are ordered and how the flow of time itself might have been influenced by the dynamics of this field. In the early universe, if the inflaton field was responsible for rapid changes in the energy density of the cosmos, then it may have altered the rate at which time passed. This notion aligns with Einstein's theory of relativity, which tells us that time is not a constant, but rather it can be affected by gravitational fields and the curvature of space-time. Therefore, during inflation, the rapid expansion might have created a scenario where time itself was experienced differently, possibly leading to a unique interplay between the inflaton field and the flow of time that we cannot yet fully comprehend. Moreover, if we consider the concept of time as a dimension similar to space, the inflaton field could be seen as a catalyst that shapes not only the spatial distribution of galaxies, but also the temporal evolution of the universe. In some theories, this idea extends further to suggest that time could emerge from quantum fluctuations in fields like the inflaton, meaning that the very act of the universe expanding could give rise to a temporal framework, a timeline along which events unfold. This perspective opens up intriguing questions about the nature of time itself, whether it is an inherent property of the universe or a construct that arises from the dynamics of fields and particles. In addition, the relationship between the inflaton and time could also provide insights into the early conditions of the universe, helping us understand how time began and what it means for time to have a starting point. Some theories posit that prior to inflation, the universe might have existed in a state where time, as we know it, did not function in the same way. This leads recent discoveries in astronomy, particularly those related to cosmic microwave background radiation and the observations from advanced telescopes, have significantly deepened our understanding of what might have occurred before the Big Bang, a concept that has puzzled scientists for decades. The cosmic microwave background, which is the afterglow of the Big Bang, provides a snapshot of the universe when it was just about 380,000 years old, but it also offers hints about the conditions leading up to that moment. Researchers have been using sophisticated instruments, such as the Planck satellite, to map this radiation with remarkable precision, revealing tiny fluctuations that correspond to the density variations in the early universe. These fluctuations indicate how matter was distributed before the universe expanded, suggesting that there could be structures or phenomena that existed prior to the Big Bang itself. Moreover, theories such as inflation, which propose a rapid expansion of the universe just after the Big Bang, imply that there could have been a state of the universe that predates our current understanding of time and space. This notion challenges the classical view of time beginning at the moment of the Big Bang, leading scientists to explore the possibility that the universe could be part of a larger multiverse, where other universes exist with their own timelines and physical laws. Recent advancements in quantum gravity theories also play a role in these discussions, positing that time, as we understand it, may not be a fundamental aspect of reality, but rather an emergent property derived from more complex interactions. Additionally, researchers have begun to investigate the implications of black holes and their singularities, where our current laws of physics break down, suggesting that these regions might hold clues about the nature of time and space before the Big Bang. The idea of a cyclic universe, where the universe undergoes infinite expansions and contractions, is another fascinating perspective that has gained traction in recent years, proposing that time could have been looping long before our universe began its current expansion. In essence, these discoveries and theories are not just reshaping our understanding of the universe, but they are also prompting profound philosophical questions about the nature of time itself, encouraging us to rethink what we know, or think we know, about the origins of everything. As astronomers continue to push the boundaries of our observational capabilities, we may soon uncover more secrets of the cosmos, which could further illuminate the enigmatic moments before the Big Bang, offering a glimpse into the very fabric of reality itself. As we explore the vast and intricate cosmos, our understanding of time has always been a fundamental aspect of cosmology. But future technologies and emerging theories promise to reshape this understanding in ways we can only begin to imagine. For instance, advancements in quantum computing could allow scientists to simulate complex cosmological scenarios with unprecedented accuracy, potentially leading to new insights about time itself. These simulations might help us probe the very fabric of space-time, allowing us to examine how time behaves under extreme conditions, such as near black holes or during the moments right after the Big Bang, thus challenging our current notions of time as a constant, linear progression. Furthermore, the development of gravitational wave detectors like LIGO and Virgo opens up new avenues for understanding cosmic events that can alter our perception of time. As we detect ripples in space-time caused by massive cosmic events, we may gain insights into how time is affected by gravity and how it behaves on cosmic scales. These observations could lead to a re-evaluation of Einstein's theory of relativity, particularly regarding the relationship between time and gravity, and might even suggest that time could be experienced differently depending on the curvature of space-time around massive objects. Additionally, the rise of theories such as loop quantum gravity and string theory suggests that time might not be a fundamental aspect of the universe, but rather an emergent property arising from more basic timeless structures. If future experiments could validate these theories, our understanding of time could shift dramatically, leading to a view of time that is more interconnected with the underlying fabric of reality than we currently believe. Moreover, advancements in observational technologies, such as powerful telescopes and space missions, allow us to look deeper into the universe's history. By observing distant galaxies and cosmic events that happened billions of years ago, we can piece together the timeline of the universe in ways we never thought possible. This historical perspective could challenge or support existing theories of cosmic evolution, ultimately leading to a deeper understanding of how time itself has evolved alongside the universe. As artificial intelligence continues to advance, it may play a crucial role in analyzing vast amounts of astronomical data, identifying patterns, and making predictions about cosmic events. This could lead to groundbreaking discoveries about how time operates across different scales and contexts in the universe. AI could help us understand anomalies in cosmic timekeeping, such as the irregularities observed in the cosmic microwave background radiation, which might hold clues about the early universe and the nature of time itself. In addition, interdisciplinary approaches combining physics with philosophy and cognitive The concept of time before the Big Bang is a fascinating and complex topic that challenges our understanding of not just the universe's beginning, but also its ultimate fate. According to the most widely accepted cosmological models, the Big Bang marks the beginning of time as we know it, which raises the intriguing question of what existed, if anything, before this monumental event. Some theories propose that before the Big Bang, the universe was in a singular state, a point of infinite density and temperature where traditional laws of physics, as we understand them, break down. This singularity represents a boundary beyond which our current models cannot provide answers, leading to a great deal of speculation and theoretical exploration. In the realm of quantum mechanics and general relativity, various hypotheses have emerged, including the idea of a cyclic universe, where the universe undergoes endless cycles of expansion and contraction, suggesting that time may not be linear, but rather a series of recurring events. If this model holds true, it implies that our current universe is just one phase in a much larger, eternal cycle, which could profoundly affect our understanding of its fate. Instead of a singular end, like the possible heat death or a big crunch, the universe might repeatedly transition through similar phases, each time giving rise to new structures, galaxies, and possibly even new forms of life. Moreover, the notion of time before the Big Bang also intersects with theories of multiverses, where our universe is just one of many, each with its own distinct properties, physical laws, and timelines. This perspective can lead to a drastically different understanding of what the universe's fate might entail. If multiple universes exist, the fate of our universe could be interconnected with the fates of these other universes, suggesting that the end of our universe does not necessarily signify the end of everything, but rather a transition into a different state, or even the birth of a new universe altogether. On the other hand, some physicists argue that the concept of time itself may not apply before the Big Bang, leading to the conclusion that asking what happened before is a category error, as time itself could have begun with the Big Bang. This perspective raises philosophical questions about existence and reality, as it challenges our fundamental understanding of cause and effect. If there was no time before the Big Bang, then our universe's fate could be seen as a self-contained narrative, shaped solely by its internal dynamics rather than influenced by any preceding conditions. The implications of these ideas, when we delve into the universe's beginnings, we inevitably grapple with the concepts of time and existence, which are deeply intertwined in ways that challenge our understanding. The Big Bang theory, widely accepted by scientists, suggests that the universe began as an incredibly hot, dense point around 13.8 billion years ago, and from that moment, space itself began to expand. This expansion marks the beginning of time as we know it, but an intriguing question arises. What existed before this event? In traditional physics, time is often seen as a linear progression, a sequence of events leading from the past to the future. However, when we consider the universe's origins, we must confront the notion that time itself may not have existed prior to the Big Bang, which raises profound philosophical and scientific questions about existence itself. Some cosmologists propose that before the Big Bang, all of our familiar concepts of time and space may have been irrelevant, suggesting that the universe did not have a before in the way we understand it. This idea can be difficult to grasp as it goes against our everyday experiences, where one moment follows another in a continuous flow. Furthermore, some theories, such as the cyclical model of the universe, posit that the universe undergoes endless cycles of expansion and contraction, implying that time could be more cyclical rather than linear. This perspective challenges our understanding of existence, as it posits that what we perceive as the beginning could merely be one phase in an eternal process. Additionally, the field of quantum mechanics introduces further complexities to our understanding of time and existence. Quantum theory suggests that particles can exist in multiple states simultaneously until they are observed, leading to questions about the nature of reality itself. Some theorists speculate about the existence of a multiverse, where our universe is just one of many, each with its own timeline and set of physical laws. This concept pushes the boundaries of our understanding even further, as it implies that existence may be much more vast and varied than we can currently comprehend. Moreover, philosophers have long pondered the relationship between time and existence, with some suggesting that without time, existence itself becomes problematic. If nothing existed before the Big Bang, what does it mean for something to come into being? This line of inquiry leads to deep metaphysical questions about the nature of reality. For instance, if time is a dimension of the universe, can we even talk about before the universe in a meaningful way? Some interpretations of relativity suggest that time is the vast expanse of space is filled with wonders, many of which spark curiosity and ignite our imagination. One intriguing aspect of the universe is the phenomenon known as black holes, these mysterious regions in space where gravity is so strong that nothing, not even light, can escape, are formed when massive stars collapse under their own gravity at the end of their life cycles. Scientists have identified different types of black holes, such as stellar black holes, which are formed from individual stars, and supermassive black holes, which sit at the centers of galaxies, including our Milky Way. Now, you might wonder, how do we even know they exist if we can't see them? Well, astronomers detect black holes by observing their effects on nearby stars and gas. For instance, if a black hole is part of a binary system, it may pull material from its creating an accretion disk, which emits X-rays. These X-rays can be detected with powerful telescopes, providing strong evidence that black holes are indeed lurking in the cosmos. Another captivating topic is the concept of dark matter. It's thought to make up about 27% of the universe, yet we can't see it directly. Unlike ordinary matter, which makes up stars, planets, and living beings, dark matter does not emit, absorb, or reflect light, but its presence is inferred from its gravitational effects on visible matter. For example, galaxies rotate at such speeds that they should tear themselves apart, but dark matter provides the additional gravitational pull needed to hold them together. Researchers are still working to understand what dark matter is made of, with various candidates being proposed, such as weakly interacting massive particles, or WIMPs, and axions. The search for dark matter continues to be an important quest in modern astrophysics.